So in Chapter 7, we're going to deal with momentum, inertia. What's inertia mean? Newton's first law.
If it's at rest.
Yeah, kind of. Okay, so inertia means, an object in motion will stay in motion, an object at rest will stay at rest. Right? Inertia is the tendency to resist change. Right? That's what inertia means in and of itself. Tendency to resist change. So the big takeaway for this chapter is going to be collisions and how things collide and transfer energy and how they collide and what happens to them after their collisions and all that kind of stuff. But to get there, we have to talk about momentum first. So there's two types of collisions we're going to talk about. The first of which is an elastic collision. And in an elastic collision, that means these objects don't stick together. They rebound off of each other. Okay, so what would be an example of an elastic collision?
A baseball hitting a wall.
Yeah, an object hitting something and bouncing back, right? Playing pool would be an example of an elastic collision. These imperfectly elastic collisions, right, which happen in perfect physics world, that means a total transfer of kinetic energy has happened. So if we had theoretically a perfectly elastic collision of an object at rest, right, if we had something hit it, what would happen to the first object? It would stop, right? And the second object would move with its equal kinetic energy. And so it doesn't necessarily move with the same speed because it depends on their masses and all that kind of stuff. But essentially, if we have a perfectly elastic collision, we should have a complete transfer of energy as that happens, right? Sometimes we don't have perfectly elastic collisions, which would cause both of them to keep moving or things like that. But essentially, if we have a perfectly elastic collision, they should have a 100% transfer of kinetic energy. Inelastic collisions, we don't have a conservation of kinetic energy because our two objects stick together now and become one object. So in an elastic collision, after they hit, they're going to stick together and move on as one solid object. So there's kind of a combination of kinetic energy. It's not so much a transfer. Okay, so anyone have an example of what an inelastic collision could look like? Or something that we'd see every day?
Throwing a fly on a fly trap.
Okay.
Yes. Grab flies and throw them into a fly trap.
It's not everyone's first example, usually.
Yeah.
Okay, so things that stick together. This could be if you go to like tackle somebody, right, and you fall down as one object. If two cars wreck and then stick together and move, just little things like that could be inelastic collision. So as long as they're sticking together and moving together as one object, that would constitute an inelastic collision. Okay, so momentum, to solve for momentum, now we're going to move backward a little bit. So momentum helps us understand collisions. Momentum, you're going to solve by finding mass times velocity. Momentum, no, it's tricky. Momentum is a P. Yeah, P equals mv. Right, it probably has to do with like a Latin or something, I don't know.
Yeah.
Okay, or just that there's 6 other things that start with an M in physics, so they picked it up a lot. Okay, momentum is vector, which means you have to have what? Direction, right? Got to have magnitude and direction. And so with momentum, most of the time we're going to deal with positive and negative directions. So if it's moving east and north, we would consider that a positive. If it's moving west or south, we would call that a negative. We will get into 2-dimensional collisions, which we'll deal with things at an angle, just like we did with vector addition. We'll kind of look at the same type of stuff. But for now, for these problems, you really need to think about west and south as negative quantities, east and north as positive quantities. Okay. Momentum always has to be in the direction of our velocity. Okay, so since velocity is a vector and since momentum is a vector, we can't have momentum opposing our velocity, right? If I'm moving to the north, my momentum has to be moving to the north, right? So it's always in the same direction as our velocity. Right, and units for momentum are kilograms times meters per second. Okay, which means when we solve mass, what does the unit for mass have to be? Kilograms. And the unit for velocity has to be meters per second. Okay, so just make sure that you're ready to go with those conversions. Okay, kilograms and meters per second. Unfortunately, there's no abbreviation for that unit. It's just the whole thing. Okay? So we're just going to talk through these examples. If you don't want to write them down, that's okay. A big truck has more momentum than a small car moving at the same speed because it has a greater mass. Do you think true or false? True. Okay? Which is more difficult to slow down, the car or the truck?
Truck.
The truck, right? It's got a greater momentum. It's moving with greater momentum because of that mass. So to oppose that motion or to slow it down, you have a harder time slowing down the object that has a bigger mass, right? That should seem pretty self-explanatory. Okay, let's try this one. A traveler is running at a velocity of 3.2 meters per second west. If the mass is 65 kilograms, what's his momentum? It's literally as easy as it looks. Okay, there is something that we need to make sure we pay attention to. 65's in the right units, which is good. What do we need to do with that velocity? Negative 3.21 because it's west. Okay. So tell me what our final answer should be here. Okay, so you can either leave it at that negative, or if you wanted to, you could go 209 kilogram meters per second west, right? One or the other, but not both. Okay, you can't have negative and west. Okay, so one or the other. Questions here? Momentum problems are really as easy as they seem. Unfortunately, that's not where we're going to stop for this chapter. Okay? All right, a rolling boulder is found to have a momentum of 4,015 kilometers per second east, kilograms meters per second east. If the velocity is 16.4, what's the mass of our boulder? Okay, it's really just as easy as it looks here.
So wait, what is that unit called? Kilograms by meters per second?
Kilograms times meters. So it's just, yeah, you can just say it kilograms meters per second.
Okay.
Yeah. Or kilogram meters per second. Doesn't really matter, but, yeah. Yeah? Okay. Now what happens when we bring forces into it just a little bit, okay? A force is required to change the momentum of any object, and you can change the direction or the momentum of the object a couple of different ways. You can speed it up, slow it down, or you can change its direction. Okay, so you can change the momentum of an object two different ways, by applying a force to slow it down or speed it up, or by applying a force to change its direction. Okay, so Newton's second law usually tells us that force equals mass times acceleration, right? We looked at this in chapter 4. Okay, Newton's second law usually tells us that force is equal to mass times acceleration. And really, this is net force, right? The sum of all forces equals mass times acceleration. Knowing what we know about the acceleration of an object, right? Acceleration is equal to change in velocity over change in time. All we did was substitute this right here. Okay? So now our Newton's second law reads force equals mass times acceleration, but we have an expanded acceleration. So the last thing we can do here is we can look at basically just kind of rearranging this equation. Force equals mass times change in velocity over change in time, right? And what does this look like right here? M times V, right? So that looks like momentum. So now we can get our final new equation to say force equals momentum over time. Okay, and if you put that delta there, that's really change in, so you can have that as well. Change in momentum over change in time. Okay. Since it's a change in velocity, it has to have an acceleration, right? Acceleration has to have a change in velocity. So realistically, we're looking at the change in momentum here. Okay, so this might be an equation that goes on your equation sheet as well. Okay, P equals mv should go on your equation sheet as well as force equals change in momentum over change in time. Okay, so we're trying to find out now. This is what force is required to stop a wagon moving at a velocity of 5.2 meters per second north in 2.3 seconds. So we want to find out what force does it take to make that come to a stop. Okay, so delta P, right, if we go back to that walkthrough, delta P is really equal to mass times change in velocity, right? So it would look like mass times velocity final minus velocity initial, right? Does that part make sense?
Yeah.
We put all of that over time.
So it'd actually be negative, right?
Yeah, that's right, because the force would be opposing our positive motion, right? So our force, we would say, is mass times the change in velocity. So what's our final velocity here? Yeah, it's final velocity is 0, and our initial velocity is 52. So yeah, that delta would be negative 52 over a time of 2.3 seconds. Okay, remember the unit for forces is newtons. So yeah, the force again here is negative because it's opposing our positive motion. Right, we're moving north, so that the force required to bring it to a stop could be friction, it could be a brake, it could be an actual applied force of something, it could be any of those types of forces that are bringing it to a stop, but it's negative because it's opposing our positive velocity. Okay, does that number look right? Is that about what you had? Okay, good. A 55 Newton object is traveling at 36 meters per second. If the force required to bring the object to stop is negative 42 newtons, how long did it take to come to a stop? Okay, try this one on your own. What did we need to do with that 55 newtons? Did we recognize that?
Yeah, 5 by 9.
Okay, good. So to get our mass, we had to take 55 divided by 9.8, and we got about 5.61 kilograms. Okay? So to find our time, we would have plugged in our force equals mass times the change in velocity, over t. And so when our variable's on the bottom right here, remember what do we do?
Switch it.
Right, we switch those two places, so we would take 5.6 times negative 36 and get negative 202.04 divided by negative 42, and we got about 4.81 seconds, somewhere in there. Okay. Good. Good job catching this, taking that divided by 9.8. All right, so when we introduced the two types of collisions, we talked about the conservation of kinetic energy and if it was conserved or not. But in all collisions, no matter what, the total amount of momentum is conserved. Okay, so we're not thinking about it in terms of energy anymore, we're thinking about it in terms of momentum. So for both types of collisions, the total momentum in our system is conserved. Okay, so the total momentum before has to equal the total momentum of our system after. This could be for an elastic or an inelastic collision, so it doesn't matter the type. But we should have the conservation of momentum in both of these situations. Okay, so that will allow us to basically set up our equations to say momentum before equals momentum after. So these equations will be similar to our conservation of energy equations, right, where we could start with 4 terms, but maybe we don't use all of those 4, right? Okay. So this is what our collision equation could look like, right? M1v1 equals M2v2. So this is the momentum of our first object plus the momentum of our second object. And then this says M1v1 prime. This little up here is called a prime. All that means is after, post. Doesn't change the way you do the math in it at all. Okay, so it kind of looks like this little apostrophe. But M1v1 prime means this is the velocity after collision, velocity after collision. Just means after. Okay, so post-collision velocity. Okay, so for this equation right here, these ones start as separate objects, right? M1, V1, and they end as separate objects. So what type of collision would that be? An elastic. If they're going to bounce off of each other, they're going to end as separate objects. So that's an elastic collision. Okay, so this would be an elastic collision equation. This one should probably go on your equation sheet. Okay, and maybe label it as elastic. Okay, let's try one here. Find the recoil velocity of a 5 kilogram rifle that shoots a .05 kilogram bullet at a speed of 120 meters per second. Okay, does anyone know what it means when it says recoil velocity?
Like how fast?
Yeah, right, the kickback of that gun. So we're assuming here that the pulling of the trigger, right, that's the collision. That's what's happening, right? That's the after now, okay? So before I pull the trigger, both the bullet and the gun are at rest, right? So essentially, our system starts at a zero momentum, right? So our whole entire system starts at a zero momentum. So if we start setting up our variables, which I think you should always do, right? M1, which one we can choose the rifle or the gun to, or the rifle or the bullet to be the first object. Does it make a difference? Right, just make the rifle the first object because it comes first. So M1 is 5. M2 is 0.05. V1 is 0, and V1 prime is what we're solving for, right? We want to find the velocity of that gun after the collision. The second object, right, V2 starts at rest, and V2 prime, right, the bullet leaves the gun with what velocity? 120. Okay? The mass does not change for that object as we go, so that stays the same. So as we start plugging it into our equation, we would say M1 times V1 plus M2 times V2 equals, bless you. Let's just give me 1 second to finish this one.
Please report to your houses. We'll dismiss you by community shortly. Thank you.
Okay, and then we would do 0.05 times 120. Okay, so just take a stop right there. We will pick this up when we get back. So picking up where we left off, we want to find the velocity of the gun after that trigger is pulled. So the trigger is like our collision. They're going to end up apart. So we're solving for V1 prime, right? So if we have a 0 on this side, that gives us 5 V1 prime plus 6. Okay. So we need to subtract that to the other side. Negative 6 equals 5 V1 prime, and that gives us a V1 prime equal to 1.2. Okay, and this is a velocity, so we're in meters per second here. Okay, so we talked about how momentum is conserved here. So this gun has a backward momentum, the bullet has a forward momentum. So the addition of those two should add up to 0. Right? If we solve for momentum of each of those separately, the addition of those two momentum should add up to 0 because our initial system started with 0 momentum. Does that make sense? It should be the conservation of the whole system. Okay? Very good. All right, two pool balls of equal mass collide. The first ball is moving at a speed of 3.1, the second's at rest. If the collision is perfectly elastic, what's the speed of both objects after the collision? Okay, so there's a couple ways we can do this. The first of which is to put it in the equation. We talked a little bit earlier about what would happen in a perfectly elastic collision, but I'm going to show you the math to prove it. Okay? Equal mass on these pool balls. So you can either pick a random mass that is equal, right? You can make all of the masses 3 kilograms or 2 kilograms or 1, whatever you want to do, or you can just leave it as an M, right? Because algebraically they should end up canceling. Okay? let's just go ahead and say that each of these have a mass of 1 kilogram, okay, for really easy sake, right? M1 is equal to 1 and M2 is equal to 1, okay? Two pool balls of equal mass. The first is moving at a speed of 3.1, so we would take 1 times 3.1 plus 1 times 0, right? V2 was at rest. After the collision, we want to find the speed of both objects, okay? So we have a truly elastic collision going on here, but we have 1 times V1 prime plus 1 times V2 prime. So I haven't given you the equation yet to solve for if we have two variables, okay? But since we talked about in a perfectly elastic collision, what do we think would happen in this case? That's right. V1 prime would be 0 and V2 prime would be 3.1. Okay, so I have an equation for you that we could use if we didn't have equal masses. So the only way this system works is if we have equal masses. If the pool balls weighed something differently, you would have to use an equation that allows us to solve for when both are missing, and I'll give you that here in a little bit. But since we have equal masses and it tells us it was perfectly elastic, we have the ability to just switch them. Okay, so in this problem, I didn't realize it ahead of time, but our math won't work here because I haven't given you that equation yet. Okay. But it only works if it's perfectly elastic and they have equal masses, so you might want to write that down. Okay, the switch only works perfectly if it's perfectly elastic and they're equal mass. Okay? Okay, so here this one says a bat is swung with a velocity of 16.2 at a 0.94 kilogram ball moving in the opposite direction. If the ball leaves the bat at a speed of 42, what's the final speed of the bat? Okay, so we need to think about the directions here when we start labeling these things. So first of all, which would you prefer to be the first object? The bat. Okay, so M1 is equal to the bat, so its mass is 22 kilograms. M2 is the ball, which has a mass of 0.94 kilograms. Okay? The velocity of the bat initially, right, if I'm thinking about this system, I'm going to think about, like, toward the outfield, right, is the positive direction, and in toward the batter is the negative direction. Does that part make sense? Yeah. Okay, so forward, right, swinging that, it would be forward or a positive direction. So V1, he's swinging the bat toward the outfield, so that would be a positive 16.2, and V2 is coming in toward home plate, which would be a negative direction, so that means the ball has an initial velocity of negative 34. Would you agree with that? Yeah. In terms of the directions here, right? It doesn't matter which direction you choose to be positive or negative as long as you are consistent, okay? After the collision, we know the speed of the bat or the speed of the ball. We know the speed of the ball, and is it moving in the positive direction or the negative direction? Positive, because it's going out toward the outfield. So that's 42, and we're solving for V1 prime. Okay, as you're thinking through this problem, I want you to think about what you would expect the bat to do after the collision. Would you expect it to move backwards? Would you expect it to continue to move forward? Those types of things, right? Most of the time you can take a guess, and the math should prove it, right? So let's see if that's the case. If you were to guess here, what would you consider that the bat what would happen to the bat? Okay, go forward a little bit slower maybe, or would it kick it all the way backwards? Right, probably forward a little bit slower. After that bat is contacted with the ball, right, it's still going to go forward just a little bit. It might slow down, but hopefully we're still going forward. I could be wrong here, but we're going to see how it works out. Okay, so we'll do M1 times V1 equals, plus M2 V2 equals M1 V1 prime plus M2 V2 prime, which is 42. Okay. So with these problems, you have to be really consistent with direction, with that negative, all that kind of stuff. So go ahead and do the math there. So I got V1 prime to come out at about 13 meters per second. Yes? No? 12.95? Okay. So as he started his swing, as soon as he contacted the ball, the bat was moving 16.2 meters per second. After he contacted the ball, it's still moving forward, but now slowing down, right? So he's still swung all the way through that swing, but we're at a velocity of 13 meters per second. Second type of collision called an inelastic collision. Okay. Ooh, ah. Okay. So let's say this cart, the blue cart originally is at rest. The red cart comes in and collides, starting with a velocity of 24 before the collision. Okay. After the collision, they are now connected as one, right? That's what happens in an inelastic collision. They stick together, and now their masses are going to be added together. Their masses will be connected and they'll be considered one object. So we have a little bit different of an equation for this inelastic collision because afterward we don't have two separate objects, we have one object. Okay? So the only thing that's different here is that we just have a V prime, not a V1 prime and V2 prime because now after this collision they are one single object. Okay, so your equation looks like this. It's the same setup at the beginning, right? M1V1 plus M2V2, and now at the end we just add those two things together, those two masses, and we would have one prime velocity. Okay, so that is an equation probably for your equation sheet with this same scenario. Okay, if the red car has a mass of 30,000 kilograms, he's moving 24 meters per second east. The blue has a mass of 20,000. What's the velocity of the cars after the collision? Okay. So it's the same type of thing. Momentum is still conserved, which was why we can do momentum before equals momentum after. So M1 is 30,000. M2 is 20,000. V1 equals 24 and V2 equals 0. V prime is what we are solving for. Okay. With these collision problems, I would really encourage you to start setting up some sort of system of labeling all your variables. Okay, because we will start eventually dealing with two-dimensional collisions, which means we will have an x and a y velocity for each object. Right? So we would have v1x, v2x, v1x prime, v2x prime. Okay, so we would have all of these types of things for every variable. So you need to make sure you get yourself into some sort of organizational system. Okay, so 30,000 times 24, and it's moving east, so that's positive. Right, our second object's at rest. And we just have one prime velocity because they are stuck together post-collision.
The collisions always say if they're elastic or inelastic?
You might have to decipher using context clues. So it might say they stick together, right? And you would have to know it's an inelastic collision at that point. But if they end up separately, if they give you two velocities at the end, you would know that it's an elastic. But no, I don't think it will specifically say in most problems this is an inelastic collision or an elastic. Okay.
So you said we'll just have to infer.
You will have to just figure it out by context clues and figure it out by the variables given to you, right? If it asks for what's the velocity of the second object after the collision, you would know that has to be elastic because there's two different ones. Okay. Did we get it to come out about 14.4?
Yep.
Okay.
I need to leave.
Let's try this one on your own. Okay, a bullet's fired at 200 meters per second. It hits and sticks to a target that is stationary. If the mass of the target is 45 kilograms, what's the velocity of the target after impact? So do we see what's happening here?
Yes.
Okay, so now the gun firing does not have anything to do with our problem, right? We're not worried about the gun or anything itself. We're talking about a bullet that hits a target and then maybe the target moves or maybe it stands still, whatever, but it's initially at rest. Okay, so we're going to see what happens to that whole system after they collide. Okay. Do we see an issue to start here? Okay. Make sure if we don't convert that, our answer is going to be crazy, right? It won't make sense. Yeah. So let's make sure that we have the correct proportions here. Okay. Try this one on your own and see what we get. Is that about what you had?
Makes the error.
Yes.
Yeah.
Zero.
Okay, so if we combine these, we should get like 7, right? And that would leave us with, here I just added our two masses, 45 plus 0.035 kilograms. I divided that over and I got about 0.155. Should that make sense that it's going not very fast,
Yes.
right? After those two hit, it's probably going to go for a little bit and then it's honestly probably going to come to a stop. Okay, but all we're looking at is directly after impact. Okay? Any questions? I want you to think about also, because sometimes we'll get to this on the homework too, you might have situations in which you have kind of a reverse inelastic collision, which means if two objects like a ball or something is traveling and then breaks apart, right, that means they would start together and then end up separately. So you can always reverse this equation to make it work that way, right? So if I have a 10 kilogram piece and a 5 kilogram piece that are part of this ball, and when they split, right, this splits into a 10 and a 5, I could either solve it as an elastic equation saying 10 is moving at this meters per second and 5 is moving at this meters per second, right? They're traveling at the same speed and then after the collision they break, or you can just add masses together at their initial velocity. Does that kind of make sense? So you can use this equation flip-flop too if they start together and end apart. Either way, okay?